The French biologist and chemist Louis Pasteur said of wine that it can be considered with good reason as the most healthful and hygienic of all beverages. The Greek philosopher Plato had strong feelings on the subject too, saying nothing more excellent or valuable than wine was ever granted by the gods to man. Thus it may seem a mixed blessing to enophiles and beer lovers that a team of microbiologists in Belgium have used genetic mapping and CRISPR-Cas9 editing to identify the yeast genes that produce higher levels of a specific aroma in wine and other fermented beverages. Their findings, published in the American Society for Microbiology journal MBIO, link with other recent projects connecting genes to flavors. The results may be used to grow yeasts that produce new flavors in fermentation. The research identifies the genes responsible for manufacturing a compound called phenylethyl acetate, which imparts the aroma and flavor of rose and honey to a range of materials, from perfume to wine and beer. The finding adds to the understanding of how yeast plays a critical role in shaping the flavor of wine and beer. Enhancing industrial yeast strains for desirable flavors has been an ongoing challenge, says study leader Johan Thavelijn, a microbiologist at the Vlaams Institute for Biotechnology VIB in Flanders, Belgium. Yeast strains can be crossbred to select for certain genes, and so certain flavors, but the process is time-consuming, expensive, and may cause other unwanted changes in the yeast. You have to do two things, Thavelijn says. One is to improve the yeast trait that you want to improve. Second is to change nothing else in the yeast. In practice, the latter turns out to be much more difficult than the former. A crossbred yeast may work in the lab, but not in the brewery. If the fermentation is bad, you have to throw away all the beer, he says. The researchers analyzed a hybrid from two parent strains of Saccharomyces cerevisiae, or brewer's yeast, and found 4 lengths of DNA that were linked to higher production of phenylethyl acetate. Further investigation showed that alleles of 2 genes, called TOR1 and FAS2, were responsible for the highest production of the flavor compound, one involved in making fatty acids, and the other helping to regulate nitrogen. Using CRISPR-Cas9, the scientists swapped those alleles between the parent strains and observed that production of phenylethyl acetate increased significantly. For the next part of their research, Thavelijn and colleagues have partnered with a Belgian brewery to evaluate their experimental yeast strains with several batches of beer, with hopes of clearing the highest hurdle of all, the taste test.